Hey, all you cool cats and kittens. I'm going to go over the notes for Polarity and IMF. I'm doing this in 4 videos. You can find them all in the Hyperdoc. Um, I just want to go over them like I would in class. I'm going to try my best to explain them. If you have any questions, feel free to come to office hours on Wednesday. I know all the chemistry teachers do, even if you don't have me. Have office hours Wednesday 2 to 3, and they might have some other times as well. So if you have any questions, feel free to ask us at that point or email us or whatever works for you. So I'm going to start by talking about electronegativity because that relates directly to polarity. So you guys have studied electronegativity already. So you know that it happens in a covalent bond and the atoms are pulling electrons towards themselves. So although covalent is shared electrons, the electrons are not shared equally necessarily. The trend is also something that we studied in the last unit. It decreases as you go down a group and increases as you move from left to right. So that does mean that fluorine is our most electronegative element. So the closer something is to fluorine, the more electronegative it is. And this doesn't include the noble gases because they don't really bond, especially at the top. So we're excluding them. So first I'm going to talk about the polarity of bonds themselves, just individual bonds that will then talk about what happens when those bonds are part of a molecule. So for nonpolar covalent bonds, bonding electrons are equally attracted to both of the atoms. So this is true when the atoms are the same element. Okay, so that means a bond is non-polar when they are the same element. No two elements have the exact same electronegativity, so they have to be the same element for a bond to be non-polar. If they are different elements on either side of the bond, they are polar covalent bonds. That means that one element is going to pull the electrons more than the other element. And we'll talk about how to figure out which one that is and all of that stuff. That is also called a dipole. We're going to use that word a lot in these videos. So make sure you know that that means it's a polar bond. So the first thing I'm going to talk about is what happens if the bond has different elements. We just said that means it is polar. Okay, so if we have an HF bond right here, okay, ignore the fact that HF is an acid, just it's an HF bond. Is it polar or nonpolar? And it's as easy as, because H and F are not the same, it is polar. Okay? Then we need to figure out the rest of this. It says, if it is polar, which atom has a slightly negative charge and which has a slightly positive charge? And the way you do that is using the information that you have from your last unit. Whatever element is more electronegative, that's the one that's going to have the slightly negative charge. Now notice I keep using the word slightly. You can also use the word partial, partial negative, partial positive, or slightly negative, slightly positive. You don't say full positive or just positive or negative because these are still covalent bonds. You remember from earlier in the year that if it's full positive and full negative, then it is an ion. It's an ionic bond, and we're talking about covalent bonds here, okay? So it's slightly positive or slightly negative. Now, the symbol for slightly is kind of like an 8, the number 8 that you don't finish. I am terrible, as my students know, about drawing on the computer. So if you can't tell what this is, please Google it to see what the symbol is. But it's kind of like an 8 that you don't finish. It's almost like an S that you kind of connect at the bottom. So this one, because F is more electronegative than hydrogen, it's going to be slightly negative. And hydrogen, just by looking at the trends on the periodic table, as you go across, it gets more electronegative, so that means fluorine must be more electronegative, which means hydrogen is going to be slightly positive here. Now, we'll talk more about when it's closer to a full positive and full negative and stuff like that later. So for right now, this is slightly positive, slightly negative. So what I'd like you guys to do now is kind of pause the video, take a minute to do this, decide if it's polar or non-polar, and if it's polar, label slight negative and slight positive based on the trends. Remember that the one that is more electronegative is going to get the slightly negative charge, and if it's less, it's going to be slightly positive. Okay, so hopefully you did this on your own, but I'm just going to go over it real quick. In F2, it would look something like this. There would be a bond with one F on one side and one F on the other. Because these are both F, that means this is nonpolar. So if it's nonpolar, then you don't need to label the slightly negative and slightly positive because there isn't one. There's no partial charges on a nonpolar bond. Now here, they're different. C and O are different, so that means it's polar. So then you look at your periodic table and figure out which one is more electronegative, carbon or oxygen. Because the period trend for electronegativity is that it goes up as you go from left to right, because oxygen is further to the right, it's going to be more electronegative. So they're going to make oxygen the slightly negative and carbon the slightly positive. Okay, and that's that. Sorry, the dog downstairs is upset because his parents left, and so now Tilly is crying with him in solidarity, apparently. So one thing I want to just make a note of is that polarity, I'm going to go into polarity of molecules and I'm going to use the Lewis structures because most of the time they work fine, and it's just easier to do it that way, I think. So I just want to make a note here that the Lewis structure doesn't tell the whole story. You need to know the geometry to figure out the whole story. And so if you want to know more about molecular geometry, I did put a video at the bottom of the hyperdoc, so you can take a look at it. We did not get into that in my class. I think some others classes did. So if you already know about geometry, you don't have to worry about it. There's just one molecule that I'm going to make sure you know, and I'll do that at some point in another video. Water is one that you need to know that whether it's polar or not, even if the Lewis structure says something different. So first, let's just talk about the Lewis structures. With a molecule, it is non-polar if it's symmetrical, meaning it's the same on all sides. And that's because all of the dipoles cancel each other out. It's not because they're not dipoles in there, okay? So don't get confused because I just said that this CH bond is going to be polar, right? Because C is on one side and H is on the other. So the CH bond is polar. But the thing is, so is this CH bond. It's also polar. And they're polar in different directions, right? So this one, the electrons will be coming towards the carbon this way because carbon's more electronegative. And in this one, the electrons will be coming towards the carbon this way. So they will cancel each other out. Same thing for this side. We're going to go this way. And then over here, we'll go this way. And they will cancel out. So the overall molecule is non-polar. Okay, and that's because it's the same on all sides. This one is not symmetrical because although these two are going to cancel each other out, there's nothing to cancel. There's no other bond in the opposite direction to cancel this one. Okay, so this one is going to be polar. All right, and you could put the slight negative and slight positive charges on this if you wanted. These two would cancel each other out, so we would just do it for the N and this H. So this would be negative, and this would be positive. but you don't have to. The question didn't ask you for that. So just one quick note about this one, that just to go back to this one. So it is the same on all sides, but if I replaced this with a BR instead, now it's not the same. Okay, so now it's not the same on all four sides. So this is a polar molecule. So it's not enough that there's a bond on all four sides, it needs to be the same exact bond. So before, when it was all H's, that's nonpolar. But here, when one of them is a BR, that's polar. All right, so again, go ahead and stop the video. Draw the Lewis structures for these two, or if you don't quite remember Lewis structures, just Google the Lewis structure and just label it as polar or non-polar. So here's SIBR4. Ignore these little arrows up here. I just screenshotted this from a website. So this is the same on all sides. So it is going to be non-polar, SIBR4. And this is PBR3. So just like NH3 before, it is going to be polar because there's not anything up here canceling what we have on the bottom. Okay, and now you might start to notice that if there's even subscript, non-polar, odd subscript, polar, that is true a lot of the time, but it's not true all of the time. So you still need to be careful with that. So do out the Lewis structure, make sure it's actually polar or non-polar. Okay, that's it for this video. On the next ones, we'll start putting this to use and telling you what that means in the real world.